You think you understand ice. You've been putting it in drinks since you were 5 years old. You've watched it melt. You've slipped on it. You've seen icebergs in documentaries, glaciers in photographs, frost on windows. Ice is familiar. Ice is ordinary. Ice is boring. But let me ask you something. Why does it float? You'll say, because it's lighter than water. Fine. But that's not an explanation. That's just restating the observation in different words. Ice floats because it's less dense. Ice is less dense because it's lighter per unit volume. Ice is lighter per unit volume because it floats. You're going in circles. You're not explaining anything. You're just putting new labels on the same mystery. So let me ask again. Why is solid water less dense than liquid water? Stop. Think about that for a second. In almost every other substance in the universe, the solid form is denser than the liquid. Iron, lead, copper, aluminum, wax, mercury, sulfur, you name it. When they freeze, they sink. The solid drops to the bottom. That's the rule. That's what matter does. Water breaks the rule. Water says, no, I'll do it differently. And nobody seems to find that strange. Nobody seems to find it remarkable that the most common substance on the surface of this planet does something that almost nothing else in the universe does. Ice floats. And because ice floats, life exists. Let me show you why. Start with atoms. Everything is made of atoms. You know that. But do you really understand what that means? Do you understand that right now, the air around you is filled with tiny particles moving at hundreds of meters per second, bouncing off your skin, bouncing off each other, bouncing off the walls? Do you understand that the glass of water on your table is a churning chaos of molecules, vibrating, rotating, colliding, never sitting still? The atomic hypothesis is the most powerful idea in all of science. If all scientific knowledge were destroyed and only one sentence could be passed to the next generation, this is the sentence. All things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. That one sentence contains an enormous amount of information about the world. Now think about what happens when you cool something down. You're removing energy. The atoms are still moving, but they're moving slower. They're jiggling less. They have less kinetic energy. And as they slow down, the attractive forces between them start to win. When atoms are moving fast, they bounce off each other and fly apart. They're too energetic to stick together. But when they slow down, when they lose that frantic energy, they start to feel the pull of their neighbors. They get closer. They arrange themselves. In most substances, this arrangement is simple. The atoms pack together as tightly as possible. They fit into neat rows and columns, like oranges stacked at the grocery store. The solid form is just the atoms sitting still, packed close, locked in place. Less motion means less space between them. Less space means higher density. Higher density means the solid sinks. That's the normal story. That's what happens with almost everything. Water is different. Water molecules have a strange shape. They're bent. Two hydrogen atoms stuck to one oxygen atom at an angle, not in a straight line. And because of the way the electrons are distributed, the molecule has an uneven charge. The oxygen end is slightly negative. The hydrogen ends are slightly positive. This doesn't sound important. It changes everything. These charged ends mean water molecules stick to each other in a very specific way. The positive hydrogen of one molecule is attracted to the negative oxygen of another. They form what we call hydrogen bonds. Not as strong as the bonds holding the atoms together inside the molecule, but strong enough to matter, strong enough to change the behavior of water completely. In liquid water, these hydrogen bonds are constantly forming and breaking. The molecules are moving around, tumbling, rotating. A hydrogen bond forms, lasts for a tiny fraction of a second, breaks, reforms somewhere else. It's a dynamic chaos. The bonds are there, but they're temporary, fleeting. The molecules are close but disorganized. Now cool it down. As the temperature drops, the molecules slow down. They have less energy to break those hydrogen bonds. The bonds start to last longer. The molecules start to settle into more stable arrangements. And here's where the magic happens. The most stable arrangement, the lowest energy configuration, is not to pack the molecules as close as possible. The most stable arrangement is a crystal structure where each water molecule is connected to four neighbors through hydrogen bonds. And this structure has gaps. It's open. It's spacious. It's like a honeycomb or a lattice with empty space built into the geometry. When water freezes, the molecules don't squeeze together. They lock into this open crystalline structure. And because the structure has gaps, ice takes up more space than the same amount of liquid water. More space means less density. Less density means ice floats. That's the answer. That's the mechanism. But if you're satisfied with that, you're missing the deeper point. Why does the most stable arrangement have gaps? Why does nature prefer this open structure over a tightly packed one? This is where you have to be very careful. This is where most explanations go wrong. People want to say because hydrogen bonds are directional, or because of the geometry of the water molecule. And those statements are true, but they're not really explanations. They're descriptions. They tell you how it works, not why it works. The honest answer, the physicist's answer, is that we don't know why in any ultimate sense. We can describe the forces. We can calculate the energies. We can predict what the stable structure will be. But when you ask why those particular forces exist, why electrons arrange themselves the way they do, why the laws of quantum mechanics have the form they have, you're asking a question that physics cannot answer. We can tell you that water molecules form this open structure because it minimizes the energy of the system given the particular forces involved. We can show you the equations. We can make predictions that match experiment perfectly. But we can't tell you why the universe has these particular forces rather than different ones. This is uncomfortable. People don't like this answer. They want a story that ends with something familiar, something they already understand. But at some point, every chain of explanation hits bedrock. You reach the fundamental laws, and all you can say is, this is what we measure. This is what the universe does. The universe doesn't owe you an explanation. It just is. Now, let me show you why this matters. Let me show you why ice floating is one of the most important accidents in the history of life. Imagine water behaved normally. Imagine solid water were denser than liquid water, like almost every other substance. What would happen in winter? The surface of a lake would cool down. The cold water would sink to the bottom. Warmer water from below would rise to the surface, cool down, and sink. The lake would keep turning over, mixing, the cold water always dropping to the bottom. Eventually, the bottom of the lake would reach freezing temperature, and it would freeze from the bottom up. The ice would form at the bottom and stay there. More ice would form on top of it. The lake would freeze solid from the floor to the surface. Every winter, every lake frozen solid. Fish would die. Plants would die. The organisms at the bottom of the food chain would be destroyed. The entire ecosystem would collapse. Every single winter. But that's not what happens. Because ice floats, it forms at the surface. The ice stays on top. It acts as an insulating layer, slowing down heat loss from the water below. The liquid water underneath stays liquid. Fish survive. Life survives. The difference between a world where ice floats and a world where ice sinks is the difference between life and no life. And it's not just lakes. Think about the oceans. Think about the polar ice caps. If ice sank, the Arctic and Antarctic would not have floating ice sheets. The ice would sink to the bottom and stay there, accumulating for millions of years. The ocean circulation patterns would be completely different. The climate of the entire planet would be transformed. The fact that ice floats is not a minor detail of chemistry. It's one of the fundamental reasons this planet is habitable. You might be tempted to say there's something special about this, something designed, something purposeful. But be careful with that thinking. The universe has billions of planets. Most of them are dead. Most of them have no liquid water, no floating ice, no life. We happen to live on one of the rare exceptions. It's not that the universe was designed for us. It's that we could only evolve on a planet where these particular conditions happen to exist. If ice didn't float here, we wouldn't be here asking the question. This is what's called selection bias. You're not seeing a miracle. You're seeing a sample of one, selected precisely because it's the kind of place where observers can exist. But let's go deeper. Let's ask what this tells us about the nature of matter. The behavior of water is determined entirely by the properties of atoms and the forces between them. The way water molecules attract each other, the way hydrogen bonds form, the geometry of the crystal structure, all of this emerges from the fundamental laws of physics. You don't need to invoke anything special about water. You don't need water to know how to form crystals. You don't need any intention or design. You just need atoms following the laws of physics, and the large-scale behavior emerges automatically. This is one of the most profound ideas in all of science. Complex behavior emerges from simple rules. A single water molecule has no concept of density. It has no concept of floating or sinking. It's just a tiny arrangement of three atoms feeling forces being pushed and pulled by its neighbors. But put a trillion of these molecules together, and suddenly you have ice that floats. You have insulating layers. You have habitable planets. You have life. The complexity comes from the numbers. The richness comes from the interactions. The behavior of the whole is not programmed into any individual part. It emerges. This is how physics works. This is why understanding atoms gives you power over the large-scale world. Because once you know how atoms behave, you can predict, in principle, everything that follows. Now let me tell you about something that should bother you even more. I said ice is less dense than water. That's true at normal pressure. But at very high pressures, something strange happens. You can crush ice into denser forms. If you squeeze hard enough, you can force the molecules closer together than they are in liquid water. There are actually many different forms of ice, different crystal structures that exist at different pressures and temperatures. Some of them are denser than water. Some of them would sink. On other worlds, under different conditions, ice might behave completely differently. This tells you that the behavior you're used to is not universal. It's not fundamental. Specific to the particular conditions on the surface of this planet. Change the pressure, and ice becomes something else entirely. The universe is larger than your experience. The rules that seem absolute to you are actually just the rules for this particular corner of space, this particular range of temperatures and pressures, this particular slice of reality. This should humble you, and it should excite you. Let's return to the atoms. Think about what's happening at the surface of a frozen lake. Below the ice, there's liquid water. The molecules are moving around, bouncing off each other, forming and breaking hydrogen bonds in a chaotic dance. At the ice-water boundary, something remarkable is happening. Molecules are constantly crossing from liquid to solid and back again. Some molecules from the liquid stick to the ice and become part of the crystal. Some molecules from the ice break free and rejoin the liquid. It's not static. It's not frozen in time. It's a dynamic equilibrium. The ice is constantly dissolving and reforming at the surface, but on average, the amount of ice stays the same. This is what equilibrium means, not that nothing is happening, but that everything is happening at equal rates in both directions. The forward process and the backward process are balanced. If you cool the water more, you shift the balance. More molecules join the ice than leave it. The ice grows. If you warm it, the balance shifts the other way. More molecules leave than join. The ice melts. Temperature is just a measure of how fast the molecules are jiggling. Higher temperature means faster jiggling, which means more molecules have enough energy to break free from the crystal. Lower temperature means slower jiggling, which means more molecules get trapped in the solid. This is the microscopic story behind every phase transition you've ever seen. Melting, freezing, boiling, condensation. It's all about atoms jiggling faster or slower, forming bonds or breaking them, finding the arrangement that minimizes energy given the available thermal motion. You don't need magic. You don't need special substances. You just need atoms following simple rules, and all the complexity of the material world emerges. Think about this the next time you drop ice in your drink. Those cubes floating at the surface are not just frozen water. They're a demonstration of quantum mechanics in action. They're a consequence of the particular shape of the water molecule, which is determined by the arrangement of electrons, which is governed by the Schrödinger equation, which is one of the fundamental laws of the universe. The ice in your drink is connected through an unbroken chain of cause and effect to the deepest laws of physics we know. And you thought it was boring. Let me tell you one more thing that should change how you see this. When ice forms, it releases heat. When ice melts, it absorbs heat. You know this from experience. You put ice in your drink to cool it down. The ice absorbs energy from the drink, melts, and the drink gets colder. But think about what's happening at the molecular level. When a water molecule joins the ice crystal, it locks into place. It forms hydrogen bonds with its neighbors. Those bonds have lower energy than the free molecule had in the liquid. The excess energy has to go somewhere. It becomes heat. It gets released into the surroundings. When a water molecule breaks free from the crystal, it has to break those bonds. That requires energy. The energy comes from the surroundings. The surroundings cool down. This is why ice cools your drink. Not because ice is cold in some abstract sense, but because the act of melting requires energy, and that energy is pulled from the liquid around it. The sensation of cold is not the presence of something, it's the absence of something. It's energy leaving, heat flowing out, molecules slowing down. This is one of the great conceptual shifts in understanding thermodynamics. Cold is not a thing. Cold is less heat. Darkness is not a thing. Darkness is less light. Silence is not a thing. Silence is less sound. The universe is made of positive quantities: heat, light, energy, matter. The negatives are just absences, just less of the positive. When you understand this, you understand something deep about how the world is constructed. Now, here's the question you should be asking. We've explained how ice floats. We've described the mechanism. We've connected it to atoms, to forces, to energy, to the fundamental laws of physics. But why those particular laws? Why does quantum mechanics have the form it has? Why do electrons arrange themselves in the particular ways that create the particular bonds that give water its particular properties? I don't know. Nobody knows. At some level, physics is not about answering why. Physics is about describing how. We observe the universe, we find patterns, we write equations that capture those patterns. We use those equations to make predictions. The predictions match experiment. The equations work. But when you ask why the equations have this form rather than some other form, you're asking a question that goes beyond physics. You're asking about the nature of existence itself. Some people find this unsatisfying. They want a final answer, a complete explanation, a story that ends with something familiar and comfortable. But the universe is not obligated to be familiar. The universe is not obligated to be comfortable. The universe just is, and the fact that we can understand it at all, the fact that we can trace the behavior of ice floating back to the quantum mechanical properties of atoms, the fact that we can explain so much about the world starting from so little, that is the real miracle. Not that the universe makes sense, but that we can make sense of it. Ice floats because water molecules form hydrogen bonds. Hydrogen bonds exist because of the way electrons are distributed in water molecules. Electron distributions are governed by quantum mechanics. Quantum mechanics is described by equations that match experiment. Why those equations? We don't know. But we can predict with exquisite precision exactly what water will do under any conditions. We can predict how ice will form, what shape the crystals will have, what density they will achieve, at what temperature and pressure the transitions will occur. That's not nothing. That's not a failure to explain. That's power. That's understanding. That's the ability to manipulate nature, to predict its behavior, to build technology, to create things that work. Understanding in physics doesn't mean philosophical satisfaction. It doesn't mean matching your intuition. It means predictive power. It means control. And by that standard, we understand ice very well indeed. So the next time you see ice floating in your drink, don't just see frozen water. See the hydrogen bonds locking into their open lattice structure. See the energy being released as molecules join the crystal. See the quantum mechanical forces governing the behavior of electrons. See the connection to the fundamental laws of the universe. See the strangeness that makes life possible. See the beautiful accident that you exist to witness. Ice floats. And that tiny fact, that seemingly boring piece of everyday experience, is a window into the deepest structure of reality. The universe doesn't care why ice floats. The universe just arranges atoms according to the laws of physics. But you can care. You can look at a floating ice cube and see the entire history of cosmic evolution, from the Big Bang to the formation of stars, to the creation of heavy elements, to the chemistry of water, to the biology of life. It's all connected. It's all one story. And ice floating is just one chapter, a chapter that happens to make your existence possible. That's not boring. That's magnificent.